Assalamu alaikum wa rahmatullahi wa barakatuhu. Friends, welcome back to my channel. In this session we will see this 300 watt power supply. It is using TL494 IC, secondary side SMPS controller. Here it have input filter circuit, EMI circuit, then it have 110 and 220 volt option, then it have DC rail. In DC rail it is using two capacitors which are in series for 220 volt option, and then it have half bridge driver. It is using D13009K transistors, NPN transistors. It have a pulse transformer, and pulse transformer is driven by this TL494 secondary side regulator. Then this driver, power driver, it will drive this SMPS transformer. This will provide output in the output side, which will be rectified from this rectifier, filtered, and then it is provided in the output. The feedback loop for the voltage, it will provide the voltage compensation, and then it have a current shunt sense line. It will give the current feedback to this TL494 error amplifiers, and it will compensate the voltage and current effect. So it will provide 12 volt. It will provide from 10.5 to 15 volt and 25 ampere in the output. So maximum 300 watt output power we will receive. Using reverse engineering method, I draw its circuit diagram, because these industrial power supplies are not provided with diagrams or service manuals. So I draw this circuit diagram and I make three portions of this diagram to understand it easily. We will see its function, its troubleshooting procedure, and what are the most common faults which are being observed in the repair process. Let's start. If you have not subscribed my channel, I will request to subscribe it. Press bell icon button for all so that you will be notified for my every new video. When we see this power supply, this combination, it is called EMI circuit, electromagnetic interference circuit. It protects from overcurrent, overvoltage, over frequency harmonics, any type of noise which is arriving in the AC line in the 60 Hz, in the 50 Hz, that will eliminate it here and it will ground it here. If it is high voltage strike, at that time these capacitors will become short circuit internally, and these will cause to blow this fuse. So this fuse will blow away so that the next circuit will protect it. Let's see step by step. In this diagram we have fuse 5 ampere to 50 volt. We have line and neutral and grounding point, chassis earth. So ground point is connected to the chassis directly, so earth ground must be connected all the time. This current will pass from this fuse. If our power supply does not start at all, at that time what we will do, the first function, we have to check the continuity. It will give continuity. If it is giving continuity, that means the fuse is good. Then the next thing, set multimeter to ohm. It is the cold testing. Check the input resistance, both terminals. It is 515K and it is increasing. That's good. If it is less than 50K, we can say 10K, 2K, or less than that, that means the power supply has damage. So it is increasing above 500K, that means the circuit is safe. It is the first indication for the circuit. If we cannot find the resistance, at that time we need to check this fuse and the next circuit. If the fuse is good, then we have RLC. This is EMI circuit, electromagnetic interference circuit, class X. Capacitor is connected here, so it is differential mode noises. If the noise will come on both lines, line and neutral, so at that time this tank circuit it will remove that noise, external noise or any switching noise from inside. So this is our barrier. It will not allow any noise, any high frequency noise to inside the circuit or any noise to go outside the circuit. So it will block all the noise here, because at high frequency the capacitive reactance becomes low. So any high frequency noise will be removed here. Then we have another set of capacitor, that is class X capacitor. It is connected in the both lines. If we see this capacitor, class X capacitor, that is yellow capacitor, is 0.1 microfarad, 275 volts. It is connected between line and neutral. If any noise, differential mode noise, will come here or it will be generated here in the line and neutral, it will be removed from this capacitor or from this capacitor. And if there is some common mode noise in any line, high side or low side, this will be removed from this class Y capacitor, that is 100 nano capacitor. This is our chassis line here. Blue capacitor, it is connected between line to earth, to the chassis, and neutral to the chassis. If we have high frequency over voltage noise, this yellow capacitor will become short circuit, its internal impedance will decrease, so that if continuous strikes are arriving in the input line, at that time this capacitor will become heat up and it will cause to overcurrent flow in the line to neutral, internal here, so it will cause to blow away the fuse. Most of the time when there is a lightning arrest or like that, these capacitors become short circuit. So if there is a continuity here, if we are replacing the fuse and if the fuse is burned out and we replace the fuse, again we find the continuity here in this line, at that time we have to check these two components. After that there is a bridge rectifier. From this point, fuse to this dual line filter, that is this one. So it will allow to pass the current from line to this end and neutral to this end, and it will reach in the center 2 points of this bridge rectifier. It is KBL 406, 4 ampere 600 volt bridge rectifier. So it will provide the rectified voltage in the output here. When the voltage will rectified from this negative line, the bridge rectifier have one cut side, one corner have cut side. So this is the positive side, and the opposite side, which is 90-degree angle, so it is the negative output. So positive output, that is here, it is reaching at this point, and the negative side from this partition, if we see this partition, there is NTC, negative temperature coefficient resistance, that is 10D11. So it will allow to pass the current to this pole. Positive here, the negative voltage through this NTC will reach here. If you forget about this line, the negative through this NTC will reach to the negative side of this capacitor, and positive end will reach to the positive end of this capacitor. So these both capacitors will become in series. When the capacitors are in series, these behave like two resistors in series, that is voltage divider. So this combination will also work as a voltage divider network. If we are applying 220 volt, 220 multiply with 1.414, 220 multiply with 1.414, it is 311 volt. And if we have 311 volt and we have voltage divider, we are using two capacitors in series, so it will divide by 2. So 155 volt will at each capacitor. 155 here, 155 here. If you will measure in the both ends from positive to negative, so we will receive 310 volts. Let's check. If you don't have a good practical experience in power electronics, never try to repair any circuit, because the live voltage are present here. We will connect line. I am using series lamp. When you are working on some boards, some circuits, always try to use the series lamp. When the power is applied, never touch to any component here, because these are unisolated voltage. We will see the lamp. The lamp will glow for the time and it will turn off. If we have something wrong in the circuit, at that time the lamp will glow fully. So that will indicate that there is something wrong in the circuit. First of all, we will check the AC voltage. AC voltage at the input side, that is 233 volts. Then check voltage across the fuse, 4 millivolt, that is nothing. If the fuse will open, if we will find all the voltage here, 233 volt to 230 volt here across the fuse, that means the fuse is open. In electronics, in electrical circuit, when there is full voltage, that means that is the open point. So this time the fuse is good. It is dropping just only millivolt, so that means the fuse is good. Then we will find these voltage at the input of this dual line filter, 233, that's nice. Then the power will move to the output side. It is 233, that's nice. Then we will check the voltage at input of this bridge rectifier. It is 233 volts. Until here we were receiving AC voltage, but after bridge the voltage polarity will change to DC. Here is alternating current and here is direct current. Now we will check DC voltage in the output side of the bridge rectifier. It is 330 volt DC and these voltages are stable. This is positive side. As I said, it is a voltage divider network. So positive here, negative after passing this NTC, the voltage are reaching here. It is 330 volt. This is our negative rail. And this is the center point, the common point, 165 volt. The total voltage are 330 because we calculated at 220 volts. Now we will see at 230 volts. We have 233 volts in the input. Multiply 1.414, that is 330 volts. Divided by 2, 164 volts. Positive, negative. This is now 165 volt. This line is less positive than this line because this is positive and this is now the low side. And this line, now this line 165 volt. This is the low side, the negative rail. This is the center value, 165 volt. So we have a center taped voltage here. If we see in the diagram, this is the ground line. This is 160 volt and this one is 320 volt. So we have two type of voltage. Ground 160 volt, 320 volt. Now we have to understand a very useful point here. In normal discussion we say this is the ground level. So this is the ground level and this is the positive rail. It is 164 volt and this line it is 320 volt. So positive, more positive. But in this half bridge topology, this ground line is not a ground line. The ground line will be considered this center point. So this end is 165 volt positive, and when the switch will change to this line, so it will provide minus 165 volt because this is positive, this is negative with reference to this, but this line is more negative with reference to this because we will take this reference point in the next circuit, because in half bridge circuit this common line is considered as return line. In normal power supplies the ground line is considered as a return line, but no, here the voltage will swing from ground to positive and ground to negative. This line will considered as a ground. Now I remove power. This circuit, it have bleeder resistors, 150k, 150k, two resistors, and each resistor is in parallel to each capacitor, so that the voltage will decrease automatically. These capacitors will discharge after fraction of seconds. So it is dropping now 20 volt. It was 165 volt. So these resistors are installed here. In some cases these resistors become open at that time. This capacitor will not discharge automatically. That can cause to electric shock or like shock hazard. So we have to check these resistors. Now this is our one checkpoint. If we are applying line voltage, we will multiply with 1.414 and we will receive the voltage here. These voltage must be divided, and equivalent voltage which we calculated, these must be available at these two capacitors. If we are not finding the voltage here, or we are finding a big variation here, that means these capacitors are internally opened or their ESR value is raised, so that it will not store the charge properly. In that case we will replace these capacitors. It is a very common failure. This is positive 320 volt, this is ground line, so this is our return line. Now in normal case we say this is the ground line, but now our ground line is here, and if we see there is a capacitor here 2.2 nano, that is here. It is connected from the center line, return line. I will say return line, that will mean this center value, center point of the capacitors. So it is connected to transformer winding. So this is our return path. Because this power supply, it is high output power, 300 watts. For 300 watt converters, it is difficult to maintain the voltage. If you have a good design that may have the PFC circuit, power factor correction circuit, so that power factor compensation will compensate the input line variation. If the voltage are varying from 110 volt to 230 volt, 240 volt, so that will compensate and that will maintain the voltage at DC range. So in that case, the cost of the converter will increase automatically, because the PFC circuit is a second power supply in that design. So here is a facility provided. If we are working with 220 volt, we will put this switch in off position in this condition. So the neutral voltage are provided to bridge and line voltage are provided to the bridge rectifier 220 volt. So it will rectify the same voltage it will provide here. But if we want to use this power supply in 110 volt operation, if we have 110 volt supply, in that case we will turn on this switch. When this switch is set to 110 volt, what will happen? This is called 110 volt link, 110 link. In that case, this neutral line will switch from this switch to the center point of the capacitor. Neutral line will switch directly to the center point of the capacitor. We are providing 110 volt. When we were providing 220 volt, this switch was off. 330 volt were provided here, so that the capacitor were getting 330. These were dividing by this series connection, but now we connected this line directly here, and one line will reach here. Now this bridge rectifier will work as a half wave rectifier. Now it will rectify this. Now this diode will used to rectify the voltage, and we will take positive voltage here. Meanwhile, the negative pulse, the negative cycle will rectify it by this diode, and we will take negative voltage here. So this common point is now provided to the capacitors, center point, and we are receiving the positive voltage here and the negative voltage here from the single line. Now the positive peak will transfer through this diode to this capacitor. The negative cycle will provide it to this capacitor. So we will take the same voltage at these 2 points. As I discussed, this is our return path. This is ground. But here, this is our return path. So here it is 160 and this is minus 160 volt. Now we will see its function. As I discussed, this power supply is using secondary side PWM controller, that is TL494. So this IC will oscillate. It will switch these 2 transistors. It will drive this pulse transformer. At that time, it will drive these transistors. When it will drive these transistors will drive this transformer, and we will receive voltage in the output section. Positive voltage are reaching to this transistor. It is D13009K. And the negative voltage that are reaching to emitter of this transistor. So collector and emitter, these will receive full voltage, positive to negative. Positive voltage are applied here, negative here. So these are open now. And if we see combination, collector of this transistor is connected to emitter of this transistor. Positive voltage are provided to collector and the negative voltage are provided to emitter of this transistor. These 2 points, collector of this transistor is connected to emitter of this transistor. Now this combination, it have its base drive components. We have 2 resistors here, 150K, 150K in series, and we have 2.2K resistor. That is the base biasing network. Then we have pulse forming network for the base. We will drive this transformer by a switching signal. The same configuration is here. We have 2 resistors, 150K, 150K, 2.2K, and this is pulse forming network. 1 capacitor, 4.7 micro, 1 diode, and 10 ohm resistor. These 2 transistors will work opposite to each other. Why? Because this transformer is providing 180 degree out of phase output to these transistors. If this is positive signal, at that time this will negative because it have 180 degree out of phase output. If this will positive, at that time this will switch. At that time output of this winding will cause to cut off this transistor. This will saturate, this will cut off. When we apply power, at that time positive voltage are provided here, negative voltage are provided here. This time this return line is connected to this capacitor. That is resonant capacitor, that is coupling capacitor. It will cause to provide the pulses to this transformer. So the transformer will receive a pulsed voltage because it is a DC blocker. It will just only allow to pass the pulsed voltage. Now as the voltage are building in this line, at that time this circuit is also providing a base biasing voltage here. This pulsed voltage, instantaneous voltage, that will reach the one winding of this transformer, pulse transformer. that is here. This capacitor is connected here. This is the winding of this transformer, primary winding, from this point to this point. Then this winding is reaching at this pulse transformer. So pulse transformer, point number 2, 3 and 4. Point number 2 and 4 are connected internally to the winding, internal winding. So this is reaching here. So it will cause to start this transistor slowly. So it will take a slight pulse. It will switch. When it will switch, it will pass positive voltage through this winding to this one. This winding to this winding. So it will complete its circuit. So this capacitor will discharge in the winding. So this winding will magnetize and it will provide voltage in the output side. Because when the pulse will pass at that time, it will cause to generate magnetic field. So this magnetic field will cause to produce voltage in the secondary. Now this is the one pulse which is caused to turn on this transistor. This time when it is switched, let's come to the next page. This is the same transformer which I draw here. The same transformer is shown here. This is the primary side, this is the secondary side. From the secondary side, we have two output sections of this transformer. I am taking my black coffee as well. If you have coffee, enjoy it. Now we have these two diodes. These will provide voltage here. This is the auxiliary voltage that are provided to power up our this IC, that is TL494. So first pulse will provided this positive side transistor, this transistor. One pulse will transfer in this winding. It will cause to induce voltage here, and it will cause to induce voltage in this winding. So these two lines are connected here. Here are two diodes, one diode and two diodes. Second, these two diodes will rectify the voltage, and these voltage will provided at this VCC capacitor, that is for auxiliary voltage. Let's check. DC voltage, it is 19.7 volt. Normally it is 16 volts. Normally it is called 15 volts. Now this voltage, this rectified voltage from this capacitor will reach here to the pin number 12 of this IC. Pin number 7 is grounded. So here it is pin number 7, 8, 9, 10, 11, 12. So these are the 20 volts. These 20 volts are applied to this IC. When this IC will receive voltage at that time, it will provide 5 volt reference, that is pin number 14. Pin number 7 is ground, 14, 15, 16. So it is 5 volt. So 5 volt are applied to pin number 13. When 13 number pin is provided with 5 volt, at that time this IC will start push-pull operation. If we see now, from this point we have a capacitor here, that is the reference voltage capacitor. Now if we see this point, 5 volt, this 5 volt are provided here. After that it is provided with 5.6K and 5.6K resistor, and the second end of this resistor is connected to ground. So we have from this point to this point two resistors in series, and the center point of that resistor is connected to pin number 2. If you look at here, from pin number 13 and 14 we have two resistors, 5.6K and 5.6K. this resistor and this resistor. Two resistors in series, and it will provide 2.5 volt reference to pin number 2. So it is 2.5 volt. 2.5 volt. When it is taking 2.5 volt reference, in the same time, we have this resistor and this resistor, 100K and 820K resistor. It is taking the voltage here from this point to this point, and it is providing to pin number 15 of this IC. So it is current mod error amplifier. This 2.45 volt, these were provided to this pin number 2. It is our voltage mod circuit. So voltage mod circuit will take 2.5 volt reference, which we generated from this point to this resistor and ground. This transformer, when it is providing voltage here, the same time it is providing voltage here in the other winding, that is the output winding. It is center taped winding. We have one line here, the second output is here. It is connected to a rectifier, that is MBR 3000, 30 ampere 100 volt rectifier, that is this one. One winding is connected to one side, the second is connected to second side. The cathode is common, so we will take the positive voltage in the output from this point. From this point to this point, it is a filter. This is output filter. This is the input, and in the center side it has its output. So we will receive the rectified voltage after passing through this filter choke. It will receive here. So here we have a capacitor bank, 1000 microfarad capacitor, 4 capacitors in parallel, that is here. This is our rectifier, this is inductor, and we have 4 capacitors in parallel. Then we have 4 resistors as a bleeder resistors, as a dummy load, that is 1.2K resistor, 4 resistors in parallel that are here. These 4 resistors from the positive line to the ground side. This is our ground side. 4 resistors are here. Then this is our return line. It is the zero line, common line. It is a winding, common point, which we shown here. The common for this winding, that is the auxiliary voltage winding, that is here, and the output winding, it is here, common point. So common point is connected at this side, and it have a shunt resistance here, that is 3.9 milliohm. 2 resistors in parallel. The current will pass, the negative side current will pass from this point to here, and it is in the output terminal. When the current will flow from this to this point, it have very little resistance, that is 3.9 milliohm. It will cause to drop voltage. When it will drop voltage, this dropped voltage will translate the flowing amount of current. So this translated voltage, which are being dropped by this shunt resistance, are provided to this TL494 pin number 16. This information is provided to this IC. How much current is flowing there? We received ground. We received positive voltage here. So this positive voltage are provided to a variable resistor here. That is 1 kilo ohm. One end is grounded. The second end is connected to 2.2 kilo ohm resistance, and it is reaching here. It is also connected with 10 kilo ohm and 220 ohm resistor in series here, and with the bypass capacitor, that is 33 nano. These 3 components are here, and it is a voltage adjustment and voltage output pin. How much voltage are here in the output line and how much voltage we need? We can adjust voltage from 10.5 volt to 15 volt by means of this potentiometer, and it will make a summing point with reference to this output voltage. It will give to pin number 1 of this IC. This voltage, it is here. So the dropped voltage here will provide it to 2.2 kilo ohm resistor, and here we have two resistors here, that is 10 kilo ohm and 220 ohm, and this is the capacitor, coupling capacitor, that will reduce the noise. It will protect the circuit from false switching. So these are the positive voltage, these are provided here from this point. Here we are receiving 12 volt. From 12 volt we have one resistor, we have two resistors, and there is a bypass capacitor, and this voltage reading will reach to pin number 1 of this IC. So this IC will receive the feedback voltage, how much voltage we need. 12 volt output. From this 12 volt, 2.5 volt reference is provided by this resistor, and it is maintained here. At this point we are receiving 12 volt. As I discussed, these voltage are reaching here. Two resistors are here, so these two resistors will provide a reference here. As I discussed, we provided 2.5 volt reference to pin number 2 by means of these two resistors. When we provide a reference to pin number 2, then we provide some input to pin number 1, and we have a compensation, voltage mode compensation. There is a 47k resistor and a capacitor, 1 nanofarad capacitor, that is for feedback, that is to give a amplification factor to this IC. So this IC will maintain the voltage required at the output terminal. How much voltage we are providing here? 2.5, and we are receiving the feedback voltage here. This is adjust input, that is here. So this information, how much voltage we need, how much voltage are present in the output terminal, this summing point will provide information to this IC. So it will cause to set the duty cycle, the switching cycle of the output. Now the voltage are provided here. Meanwhile, as I discussed, the common line, it is connected to this shunt resistance or 3.9 milliohm resistors. So it will connect the ground line to the negative rail, and this is the I sense signal, current sense signal. So this current sense signal is provided to pin number 16 of this IC. It is provided to pin number 16. This end is grounded with the VCC capacitor, auxiliary bias capacitor. This side is connected to the return path of this IC, and this line, this information will transfer to pin number 1. So pin number 1 will receive how much current there is flowing. So this IC will compensate. How it will compensate? We received 12 volt without load. When we connect some load, for example, we are receiving voltage without load. This IC is switching at 10% duty cycle. We connected some load. There will a voltage drop here. This voltage drop will be sensed from this line. So the IC will start to adjust its duty cycle to maintain the voltage. Same time, how much current is flowing here, this information will also transfer to this IC. So this will protect this circuit from overcurrent switching. So this circuit will not drive to any dangerous condition, so that the circuit will never damage. Across this diode, we have we have one resistor and one capacitor that are connected here. 1 nanofarad capacitor, 10 ohm resistance, that is connected from the winding to the output side. From the winding to the output side, it is a recovery component. It is called snubber circuit, that is for recovery of this diode. So when it will rectify, its junction capacitance will cause to dissipate power. To eliminate that recovery period, this circuit is connected here. So these two components are snubber circuit for these rectifiers, so it will cause to protect from overheating of this circuit. If this power supply is not starting up, the first problem here, this capacitor will make problem. If this capacitor is damaged, it will not allow this circuit to power on. This is the basic problem in this circuit, because all the time it will allow to pass the pulsed voltage. If this capacitor is short circuit, at that time it will connect directly the center line here. If any transistor will switch, that transistor will cause to flow the full current. In that case, the transistor will damage immediately, or it will heat up quickly. In that case, we need to check this capacitor. If this voltage divider network and the startup circuit it not working properly, at that time it will not switch, because in first attempt this circuit have to switch. Then we have here the resonant circuit, 30 ohm resistors and 2.2 nano capacitor, 3 resistors in parallel that are here, and 1 capacitor that is here. It will discharge this winding within the specified time. In initial start, we need to check the voltage here at these two capacitors, 160 or 150, like that. If we are working at 220 volt, at that time it will around 161 volts. Here. If we cannot find the voltage here, might be we have something wrong in this portion. We need to check AC voltage here. If we don't have AC voltage here at the input terminal, that means there is something wrong in this portion. And if we have voltage here at this point, 329 volt, and the voltage are not reaching here, in that case we need to check this NTC. This time it is dropping 0.1 volt, so that means it is working now. If it is dropping too much voltage, all the supply is dropped here, that means this NTC is damaged. If it is damaged, it will not provide path to the electrical current. So we need to test this NTC. Sometime when the capacitors are internally leak, these will cause to increase its resistance. Most of the time it will blast, it will come in two pieces, it will be separated. So at that time we need to check this NTC, that is here. Then most of the time these capacitors make problem. When we test normally, we can find the voltage, but when we connect load, this IC will start to fluctuate. At that time we need to verify these capacitors. Sometime its internal ESR value is increased. When it is increased, at that time these capacitors will not provide a full current to these switching devices, these transistors. So these transistors will not switch properly, and it will not provide a required magnetic field in the winding. So this transformer will not provide required output in the output side. This is the second fault. If we are working in 110 volt At that time, if we set this switch to 110 volt here, 110 volt position, and it must provide voltage here 160 volt. If it is not providing voltage, in that condition we need to test this switch. Set to continuity, the power is removed. It must provide continuity. Why? Because it have to produce the return line to the center point. If it will not provide path to the electrical current here to the center common point, at that time it will not allow to provide required voltage to the switching devices, so that this IC will not switch properly. At that time this IC will not take a good start. Why? At that time these capacitors will drop around 60 volt. So that will not enough to produce the required magnetic field. This IC will not switch. Let's come to the point. TL494. We have pin number 1, pin number 2 that we discussed. It is error amplifier, voltage mod error amplifier. Pin number 2 that is programmed for 2.5 volt. Pin number 1 that is connected to the output terminal and the voltage adjustment potentiometer, and it will provide feedback at pin number 1. So it must be connected here to take output. Then this pin number 15, it is for current mod. Let's check its voltage because it is using pin number 7. Let's connect this multimeter because it has sharp leads, so it is good. So pin number 15, it is 36 millivolt, 2.8 millivolt, because this time it is working with no load, 2.9 millivolt DC. And pin number 15, that is 36 millivolt, just only. Why? Because this error amplifier is programmed with some different configuration, that is 100 kilo ohm resistance and 820 ohm resistance. So these two resistors are connected with 5 volt reference, that is pin number 14. So we are providing reference voltage here. If it is not taking in current sense input, that's no problem, but the voltage mod must be connected because it is just for protection. It will give the maximum input current information. Then we have compensation pin. The same, this error amplifier, current mod error amplifier, is also connected with 10 nano and 10 kilo ohm resistor to pin number 3. The same here, voltage mod 47K 10 nano, it is connected to pin number 3. There is a coupling capacitor that is for protection of fault switching, that is 1 nano between pin number 2 and 3. Pin number 4, that is dead time control. It is a protection circuit as well. Normally it is connected with 12 kilo ohm resistance to the pin number 4 and 820 ohm resistor to pin number 15. So it is connected here to pin number 4. Now the output voltage are provided here to this 12K resistor, 1.2K resistor. So it will provide a specific switching level and it will connect this ground voltage to this transistor, to this capacitor, and it will provide this switched level here at this capacitor, that is this one. So these two capacitors are used as a dead time control. Anytime when the voltage will drop, at that time this will open and it will cause to float this capacitor. When it will cause to float this capacitor, automatically this voltage at pin number 4 will raise. When pin number 4 will go high, at that time this IC will turn off because it is also working as a shutdown. Then we have pin number 5 as a CT pin and pin number 6 as a RT pin. 22K and 1 nanofarad capacitor. So this IC will switch, its switched frequency will divided by 2 and it will provided at these output transistors. Emitters of the both output transistors pin number 9 and 10 are grounded together. And these two transistors, that are 2SC1815, very common NPN transistor normally. This transistor and this transistor. These are connected to, now we are coming to this point. These are connected to this transformer. Drive A, drive B. That is here, drive A, drive B. And if we see this positive voltage, that are 20 volts, that 20 volts are provided to this resistor, that is 1.5 kilo ohm resistance, and it is connected to the center pin of this transformer, that is pulse transformer. The rectified voltage from this winding are provided here, and through this resistor it is provided to center tape winding. So one transistor is connected here, the second transistor is connected here. Collector of this transistor is connected to here, as we shown here in this winding. I will upload this diagram and you can find the link in the description. You can download it. So collector, this collector, these are connected here. And as I discussed, positive voltage are provided to 1K5 resistor and it is provided to center tape winding. So these transistors will work in push-pull drive. If this one is on, this one is off. Why? Because this IC have internal flip-flop that will switch sequentially one by one in sequence, high, low, low, high, opposite to each other. So this drive will reach here to this base, and this base is also raised with the positive voltage, that is 3.9 kilo ohm resistance and 1.5K resistor to ground. And this transistor 3.9K and 1.5K resistor to ground. So these two transistors have an offset voltage to keep them off all the time, because these are pulled up. When these are pulled up, these will remain silent all the time, just only when this signal will reach at the base, it will cause to drive. So one transistor will on, the second will off. When this is on, this is off. Both will remain on and off, opposite to each other. So one time the drive will reach here, the ground level will switch through this emitter to this drive. So it will complete its circuit to the positive voltage through this resistor. When this transistor drive A will on, at that time it will provide switching from this side. In both cases, if this pulse is coming here, it will cause to induce voltage in the secondary. Now, because here we have bipolar magnet, if this winding will go high, at that time this end will become low automatically, because it is opposite winding to each other. So this transistor, if it is working, the second will remain cut off. If this is working, the second will remain cut off. How it will work? Let's say now this transistor is switching this positive voltage are reached to the collector of this transistor. If it is on, through this diode resistor, it is biased. At that time, it will pass these positive voltage here, pulse transformer, and it will go to the winding and it will cause to pass a pulse So this will reach here to the return line. Now as we discussed positive voltage, so positive voltage, that means from this capacitor, at that time if this transistor will switch, the voltage in this capacitor will discharge this in this winding. So the current flow will from positive to this winding to the negative pole of this terminal, this capacitor. So that will cause to flow the current here when the cycle will change. So this transistor will go in cutoff state and this transistor will come in active state. So it will become activate. Now this ground line is reaching here, negative side. It will reach here, it will reach here, in this winding, it will reach here. This time the current direction will reverse, because one time the current direction will from positive to negative. The second time the current will from negative to positive. As we discussed here, if this capacitor will allow to pass the current, this is the primary voltage. When the voltage will change, cycle will change, this capacitor will allow to pass the current. At that time the voltage will switch here, one time here, the second time here. So in this condition the transformer will switch from ground to positive, ground to negative, because our this center point is the dead line, dead point, the center point, the return line. So the return point 160 volt and minus 160 volt. Let's check on the oscilloscope. I will connect oscilloscope across this winding. If you want to connect oscilloscope, always use isolation transformer. That is the best option. I will connect oscilloscope across the primary winding. Use 10x. Channel 1 10x probe. Now I connected the oscilloscope DSO in the primary winding of the transformer. This is our zero line. One transistor is switching in this period, the second is switching in this period. It is 164 volt upside, 164 downside, these peaks. So these are the oscillation of the winding, collapsing magnetic field. So this line, one transistor is switching in this period, the second is switching in this period. So the winding will receive opposite voltage. As I discussed, 160 volt peak upside, 160 volt peak downside. This time it is utilizing its minimum duty cycle to switch. Why? Because this time there is no load. When we will increase the load, at that time the voltage will drop in the output side at this terminal. It will give feedback voltage adjustment to pin number 1 of the IC. So it will receive feedback here that the output voltage are dropped due to load. So at that time this will increase its duty cycle. It will increase the switching period for these transistors, these push-pull transistors. These will drive this transformer. So it will make a wider pulses instead of using minimum duty cycle. So these transistors will switch and it will allow to switch the more time. So it will cause to allow the more wider pulses to flow the current in the primary. So strong magnetic field will build at that time. This period will increase. So this pulse duration will increase so that the output voltage will increase to compensate the load effect of on the output terminal. When you want to solder, desolder, always take care for power supply. Power supply must be removed and the voltage on this capacitor bank must be discharged. Now I will connect the return path in the secondary side, and now we will check the drive pulses. 1x. So here is 48.1 kilohertz at the CT pin. So these ramps for RT-CT. So this time this IC is switching 48 kilohertz CT pin, and when it is working in push-pull, it will divide by 2. So the output pulse must be divided by 2. Yes, it is 24 kilohertz. So these output pulses are 23.97, that is 24 kilohertz. The output transistors of this IC will switch half frequency than the CT pin, because it is working in push-pull stage. Why? Because pin number 14 and 13 are connected together. That is the output control pin. When output control pin is connected to V reference, the IC will work in push-pull to drive bipolar magnet. Now we will see different possible faults of this power supply. The first problem, these two capacitors, when the power supply is fluctuating, it is not providing a stable output. The second problem, if we have input short circuit, what we will check? Bridge rectifier, these two capacitors, these two power transistors. If these transistors are short circuit, or if this capacitor is short circuit, at that time this power supply will blow this fuse. If this capacitor, the yellow one capacitor, this one and this one, these will become short circuits, at that time it will cause to blow the fuse. These are the fuse burning. If this capacitor is internally short circuit, in that case it will cause to damage this bridge rectifier, and at that time it will damage the fuse as well. How we can verify DC rail input circuit? Set multimeter to diode mode. These are our checkpoints. Power is removed now. First of all, verify the DC voltage at these capacitors. If there are some voltage, discharge it. It is 0.8 volt. So let's discharge it manually with this screwdriver. If the voltage are high, never use screwdriver to discharge. Use some lamp or some resistive load to discharge it. Set multimeter to diode mode. Black lead to positive terminal. Connect to one input terminal, AC input terminal, one diode, 0.561 voltage drop. Second input terminal, 0.561 voltage drop. Move this lead to the negative terminal of the second capacitor. The first thing, we connected this black lead to the positive terminal of this capacitor. Now we will connect this lead to the negative terminal of this capacitor. That is here. Connect at input terminal, it must open. If it is giving continuity, that means the bridge rectifier or something short circuit, or maybe this transistor is short circuit. Swap the leads. Connect red lead at the positive terminal of the first capacitor. Second lead, black lead at input terminal. Swap the leads to both terminals. It should open. Now move this lead to this capacitor. First red lead here. Now red lead at this capacitor negative terminal. That is here. Now we can check. One diode drop 0.57, the second diode drop voltage 0.57. That means our bridge rectifier and this circuit is safe. DC rail is good. If we have something wrong in the DC rail, in the power rail, this will give short circuit. If anything is short circuit, it will give continuity. Now the second checkpoint, we must verify this capacitor, that is resonant capacitor here, to couple the voltage to the primary winding. It must open. Now we will switch to the capacitor mode. Discharge this capacitor properly. Now check the capacitance of this capacitor, 1.1 microfarad. So that's good. So this capacitor must give capacitance if it is good. If it is short circuit, it will not give the capacitance. At that time it will cause to heat up these transistors. If you find any suggestion, if there is something, maybe there is some mistake, if you observe some suggestion, some correction, it will be welcomed and I will thankful. When we work, if we understand the function of the circuit, that is the excellent work. If we want to take voltage, output voltage, and this feedback network is not working properly, these resistors, these are not providing the voltage to the pin number 1, or its compensation circuit, it is not calculated properly. That is, this resistor, the feedback resistor, it will not adjust the duty cycle, it will create the regulation issues. The power supply will not provide some regulated output. Most of the time, problematic area in this power supply, that is this section, the power transistors. These two transistors, these two capacitors, these are the most problematic items. Then the VCC capacitor. Then sometime there is a dead time issue. So we need to check these polar capacitors. If this IC is not switching at all, that time we need to test this capacitor and its related circuit. It have to produce the voltage. Then this IC will start and this IC will take control for the regulation. Another most problematic component that are these polar capacitors. Because polar capacitors, these have their limited lifespan. Internal dielectric becomes dry. When its ESR value is high, at that time it will not store the charge properly. So we need to remove the capacitors. The best way to verify their lifespan, we need to verify their ESR value. So that try to purchase a ESR meter that are not too much expensive. You can purchase ESR meter and check the ESR of the capacitors. That is the best way. If we test this capacitor with multimeter, with capacitance meters, we will take approximately the similar value around its rated value, but its functional test, that is monitored at high frequency test, that is some rated frequency, and then its internal resistance will be verified. Friends, I hope so this video is informative. If it is informative, hit the like button. If you have any question, let me know in the comment box. Thanks for watching. Assalamu alaikum wa rahmatullahi wa barakatuh.